Right, so we're going to be talking about Earth's atmosphere today. The first thing I want to do before we get started is explain a little bit about the electromagnetic spectrum. So, just to go over that so that we are kind of on the same page when it comes to understanding the electromagnetic spectrum, because it's part of what we do when talking about atmosphere. So, if you'll remember the sun, so we have our sun up here. Let's see. The sun is giving off radiation. So go back. We're going to give off, we're just going to pretend like this is sun's radiation. So you've looked at the seasons and how the sun's radiation is coming through. Well, the sun's radiation actually lets off a spectrum. All right, so we have our spectrum that comes out of the different kinds of radiation. And as it comes through, it lets off this spectrum, and we essentially have them on different frequencies, right? So we have our low frequency waves, which are called radio waves. And then we have microwaves. We have our infrared radiation, and that's typically what makes you feel hot. All right. Then we have our visible light, which is a teeny weeny little section in here. And then we have UV radiation, and there's UVA, B, and C. Then we have X-rays. And our highest frequency, our most energetic, is the gamma rays. So, all right, so just so you kind of keep those in mind as we're going through this talk today. All right, so our atmosphere, actually, Earth extends much further than you probably realize. Here we have the sun, and we have the Earth out here. Okay, so the Earth actually has another barrier beyond the atmosphere, and this is known as the magnetosphere. So the magnetosphere actually extends far out into Earth, and it's done sort of in what they call a bow shock. So the charged particles from the interior of the Earth are being given off, and most of these are electrons. Okay, so this and these are known as like the Van Allen belts, and some other terms as well in here. So what these do is they actually protect us from solar radiation. So the solar radiation comes in, and when it does, it hits the magnetosphere, and then that radiation is sent away from the Earth. All right. The two that are protected by the magnetosphere, or they're either absorbed, some of them are actually absorbed, where they go. So what we have is we have our gamma. Gamma doesn't get through at all. And then the other one is X-rays. And neither one of those, when you look at the electromagnetic spectrum, are able to get to Earth's surface because of the magnetosphere. I think it's super cool. Now, Earth is not the only one with a magnetosphere. The big gas giants out there all have really strong magnetic surfaces. So they're giving off lots and lots of charged particles. And the Earth is the only one of the terrestrial planets, the interior planets, that have a magnetosphere. Now, the Earth sits in a really interesting position. It's actually known as what's called the Goldilocks zone, meaning we're not too far away from the sun and we're not too close. So we're just right. The other thing is we're not too big and we're not too small. We're just right, which allows for Earth to exist. Now, our atmosphere is actually held in place because of the magnetosphere. Because we are protected from the sun's radiation getting through, it actually helps to hold the atmosphere in place. All right, now the Earth's atmosphere is actually an extension of Earth itself. So we usually think about the fact that we're a rock, right? We're terrestrial. And then we have this atmosphere sitting on top of us. The reality is it's all kind of one stacked system. It's all layers upon layers upon layers. And what it is basically our atmosphere is layers of gas held together by Earth's gravity and protected by the magnetosphere. So when we look at the composition of the Earth's atmosphere, what we see is that the vast majority of it is nitrogen, and most of this comes in the form of nitrogen gas, or N2. So when we looked at the nitrogen cycle, that was definitely part of it. 78% is nitrogen, so the vast majority of our atmosphere is nitrogen. The next one is oxygen. So we have 21% as O2. All right, now we use this in life. So the nitrogen we use for nitrogen fixation, and the oxygen for respiration, for cellular respiration. Now, if you added those two up, what you notice is that 99% of our atmosphere is composed of those two gases. Well, that's curious because a lot of times what we think about, especially when it comes to CO2, and as those numbers are building up and building up, wow, that must be a lot of carbon dioxide out there. But it's less than 1%. In fact, if you accounted for all of these gases, it's 1% altogether, and that includes water vapor. So we can see water vapor clearly, right? Most of the time, right? It's either as humidity or we see it as clouds and those kinds of things. Carbon dioxide is not visible to us. All right, so it's an invisible gas. Now we absolutely need them, and we need those for specific purposes. By the way, there are tons of other gases, but they're also in small number. Now, if you think about carbon dioxide, CO2, as it is in the atmosphere, the plants use it for photosynthesis. Notice what else carbon dioxide and water vapor do. They help to reduce temperature fluctuations. So when you think, if you think about the moon, for example, the moon has virtually no atmosphere whatsoever. And the temperatures on the moon, so when the moon's surface is facing the sun, the temperatures are astronomically high, like several hundred degrees. When it's away from the sun, on the dark side of the moon, or facing away, the part facing away, the temperatures plunge. So it gets really, really cold, several hundred degrees below zero. So what our atmosphere is able to do is to keep those wild swings. And that's one of the reasons why life can exist, because we have a moderated temperature because of that. Now, if you compared that to our sister planet out there, Venus actually has a really thick atmosphere. It's got a lot of carbon dioxide, and that came from old volcanoes. It didn't have plants there to start to use that carbon dioxide, so it's built up and built up and built up, and it gets hot and it stays hot. So we've never been able to send a probe to Venus because they all burn up. It's so hot. So here's the thing, carbon dioxide, we talk an awful lot about carbon dioxide, but you'll notice it's a small component of the atmosphere. So that may not make a lot of sense. Now, water vapor, also a very powerful greenhouse gas. So very powerful. And I'm gonna abbreviate this GHG, all right? So our greenhouse gas. The difference though with water vapor is it fluctuates, the levels fluctuate quite a bit. So it comes up, it goes down, like the water cycle, right? So though it's very powerful in holding in gas, it doesn't stay in the atmosphere for very long. So it comes back down, where carbon dioxide has a tendency to stay in the atmosphere for much longer. That's one of the reasons for concern. I want to make an analogy here for you. Let's think about a cake. So you're baking a cake. When you do, there are two ingredients that you use more of than any of the other. One of them is flour, right? So you're going to make a cake with a lot of flour. You're probably going to use 2 to 3 cups of flour for that cake. So that adds the body or the bulk of the cake. In a way, in our analogy, nitrogen then is like the flour of our atmosphere. It takes up a lot of bulk. The sugar, you're not going to use as much sugar, but you're going to use a cup, right? You're going to use quite a bit of sugar. And when you do, it's also going to add some density to it. So that sugar would equate to our oxygen. Now, if you add a little bit more sugar to your cake, it's really not going to make too big a difference. Now, flour, it kind of gets picky in there, but that's a whole other analogy. Okay. So what about the carbon dioxide? So it's not very much. What does that equate to? In this analogy, think about it like it's the salt. All right. So if you don't have any salt whatsoever in your cake, it's going to taste very bland. You're going to know immediately that something is wrong. But if you add more than like a teaspoon of salt, you're going to know immediately that you have too much salt in it. So that's how it works with carbon dioxide. Just a little bit extra can make all the difference. And it can make a huge difference in whether or not you want that around. So carbon dioxide is the same way. Water vapor as well. So think about water vapor like the vanilla of the cake, right? Even in a chocolate cake, you're going to put vanilla in there. You need it, right? It's going to add that something, right? So carbon dioxide and water vapor, though they're not very much, they make a big difference into whether or not you want more. Okay, so we don't want more. Now, water vapor, we can manipulate that some through some human activity, and we're going to kind of look through that as climate change happens. But the carbon dioxide, of course, is the concern there. All right, let's move on. Okay, so the Earth's atmosphere is actually 5 layers. The troposphere, which is on the bottom, the stratosphere, which is next, mesosphere, and we're going to look at each one of those separately. On this page, what I want you to notice here is this chart here on the right-hand side. And what you see here is what's going on with temperature in regards to layers. So the troposphere, notice what's happening with your temperature. So it's lower temperature here, higher temperature here. So as you go up in the troposphere, your temperature is actually going to decrease. So if you think about it, when you climb a mountain, right, the temperature gets colder and colder and colder. It's because the air is getting thinner and the temperature is going to decrease. But notice what happens in the stratosphere. That trend is reversed. And so the temperature actually turns around and goes the other direction. There's some reasons for that. We'll talk about that here in a minute. Now notice what happens in the mesosphere. In the mesosphere, the temperature plunges. It goes down significantly. So it gets really, really cold. And then finally, up in the thermosphere, heat, right? So the temperature is actually going to turn around, and quickly as you go up in the thermosphere, the temperature is going to rise, and it's going to start to rise exponentially. So you have a decrease and then an increase and then a decrease and then a wild increase. And there's reasons for that as we go through here. All right. Oh, I'm trying to move the wrong thing. So the troposphere. So the troposphere is the bottommost layer. All right, so right down here is our troposphere. And this is where life occurs. So tropical, all those things point to life. So all life occurs in the troposphere. There is a vertical mixing of gases. So what that means is that you're going to have warm air rising and cold air falling. So it sets up these convection waves. And we'll talk more about this when it comes to weather. But we have this vertical mixing of gases that's occurring. And so as the air mass goes up, it's going to rise because it's warm, but that's going to strip out, as it goes up, it's going to strip out all of the water vapor. and then it's going to get cold. And as it does, the air is going to get more dense, and then it's going to begin to fall. And we'll talk more about that later. Okay, the stratosphere. Now, strato means layers, like an onion, like a parfait, right? So stratosphere. We're going to have, so what happens here is the reverse of what happened in the troposphere. You're going to have your warm layers up higher and your cooler layers down lower. So one of the reasons for that is the ozone layer. So the ozone layer is in about the middle to upper part of the stratosphere. And what the purpose of the ozone layer is to absorb UV radiation. We're going to talk a lot about this later. Now, commercial jetliners, everything likes to fly in the stratosphere, and the reason is because it doesn't have that vertical mixing of gases. So if you've ever been on an airplane and you're flying along and all of a sudden you're like, oh, it feels like you're up and down and it's bumpy. That is because there is that vertical mixing of gases. So the air is turbulent, the air is moving. But when you get up in the stratosphere, it smooths its way out. So you don't have that happening as to the degree that you do. So that's why they like to skim that lower stratosphere so they can kind of smooth the air out for us. The ozone layer. All right, so what is the ozone layer? The ozone layer exists all the way around the Earth, okay, and it acts as a way of absorbing UV radiation, particularly UVB and UVC. Now, UVA is able to get through. That's why you wear sunscreen. But that UV radiation, now the other thing I want to say is UV radiation is not hot. It doesn't feel hot on your skin. It's an important distinction that we're going to need later on in the semester. But that UVB and UVC can be really harmful to life, and we'll talk why that's true, why they're so damaging to particularly DNA, and what's up with this. So you probably know, there is a hole in the ozone layer. There's actually two of them. The biggest one is in Antarctica, and we'll talk about why it exists there, and we will ozone the heck out of this thing as we go along. So just for now, the one on the Arctic, the Arctic ozone hole is not as bad, but anyway, we'll get there. Okay, the next layer is the mesosphere. Now, the mesosphere is called meso because it's in the middle. That's what meso means. We don't know a whole lot about it except that it's cold. We also know that this is the place where meteorites burn up. They also, whenever they're dumping things from the ISS, like they dump their trash out, it burns up in the mesosphere. Now, this is curious because we usually associate burning things with hot, right? But this is cold. So what's going on there? Remember, things burn because, in this particular case, because of friction. So there's a lot of particles in there that are causing this friction for things to burn up. And there's a lot of iron in this layer because that's what most of the meteorites are made of. That nothing really gets through here unless it's pretty sizable. So almost everything burns up as it's going through. Notice it also can protect us from charged particles of solar winds. Okay. They're studying the mesosphere as we go along. It's probably got a lot more important functions that we don't even know about. Just think about how we're protected by stuff so far. Like, life exists because of things like our atmosphere and every single layer of it. It's astounding, really, when you think about it. It is to me. Okay, so the thermosphere is next. Thermo, heat. So if you'll remember, the temperatures rise dramatically in the thermosphere. Now, in the thermosphere, this is where you're going to see the auroras. This is where they happen or where they occur. There are two, actually. We talk about the aurora borealis a lot, and that is the northern lights. But there's also the aurora australis, which is the southern lights. Now, most people don't see them because of the way our terrestrial parts of the Earth are. We have more land masses and more people in the northern hemisphere or the northern hemisphere than we do in the southern hemisphere. I want to explain to you how these auroras occur. So if we come back up here to our magnetosphere, right? So as these solar winds, so we'll have like a huge solar flare. So it'll come barreling toward the Earth, and when it does, it may make it through some of the layers of the magnetosphere, but then it's sent toward the poles like this. So it comes right around to the poles. Well, then that light, that radiation gets scattered, and it will move this direction, right? That's what causes those northern lights and the southern lights, is that they basically get in the thermosphere, and those charged particles cause all those bright colors. But they happen toward the poles because that's where the energy is sent. Okay, so it's sent toward the poles, and then it kind of scatters outward. The northern lights, if the solar flare is strong enough, they have been seen as far south as Oklahoma. So they can actually get way down. So once we get up to the thermosphere, the air is getting lighter and lighter and lighter. Remember, this is all layers, and it's all built on gravity. So by the time you get up here to the exosphere, about the only thing left is our hydrogen and helium, the two lightest elements left, and a little bit. So we have our hydrogen and our helium, and then we also have a little bit of atomic energy, oxygen left, and that's it. So what that means then is it's a really good place for things like the space shuttle to fly, or different kinds of satellites, right? They'll send those up there because there's not friction with other air molecules, which means they can go faster. Also, there's microgravity, which means they don't have to adjust the height they don't have to account for gravity as much as those are going around. Now, those two layers, particularly the thermosphere, is very, very thick. All right, so it's compared to the troposphere, which is really, really small. Like, life doesn't go up very high. Everything else above us is still considered part of the Earth system. So that thermosphere is actually much thicker than you imagine. So what that means then is that we can send satellites up into these areas without having to worry about them like bumping into each other. Now we do have a little bit of an environmental concern, and that's because we've sent so much stuff up there that we have a lot of space junk floating around. And this is a concern because as things travel around the Earth, and if there's even the smallest, like a grain of sand, is traveling at extremely high speed, and that means that other working satellites or the International Space Station are in danger of those hitting them, blowing holes in equipment, hurting astronauts as they're out there on doing their EVAs, which is their outside the vehicle activities, fixing stuff and so forth. So this is a concern. And there's talk about how do we go out and capture all that space junk that we're putting up there. If you saw WALL-E, you know, it's not that bad. It's close. Okay, that is all I have for you on the atmosphere. And yeah, thanks.